My name is Ehsan Misaghi. I am one of the co-founders and the director of research and education at the AI and Medical Systems Society, which has brought you this course. Those of you in medicine that are doing this for an elective, make sure you stay until the end to submit your attendance, and the rest of you, please also stay until the end so that you can obviously learn from what Mahdieh has to say today, as well as give us some feedback about the course and today's session. And I don't know if I think it actually went out in the email as well, so you are gonna get into a draw for gift cards at the end if you do the feedback survey as well. Okay, without further ado, I'll give the mic to Mahdieh and she can introduce herself and then tell you about the course and today's session. If you want to, you can just put this somewhere on your coat or something if you want.
I can do that, yeah.
Sorry. Does that work?
Yes, and this one's okay.
I think so. You can just ask them again.
Okay, can you hear me?
Yes.
They can't hear me. Can you hear me?
Yeah, we can hear you.
Yes. Okay. I'll try. Okay. Hello everyone. On the Zoom as well. My name is Mahdieh. I'm currently a research assistant in computer science department at U of A, and I recently graduated from my master's. And today I'm gonna talk about an overview of machine learning algorithms, and the reason for calling it an overview is that it's going to be like very general in terms of talking about algorithms, so we don't cover math or any code, and it's just like an introduction version of classical machine learning. So in our today's lecture, what we're gonna do first is to review the essential terms that we had from lecture 1. Then we're gonna talk about the machine learning workflow, which just starts from what our problem is, what our data is, and where it comes from, and what kind of model can be used to solve that problem, and how can we make sure that model is actually working correctly. So we will talk about core machine learning algorithms that are from the classical side of machine learning. So we won't be covering any deep learning materials here, and you will see them in the next lectures. And throughout this lecture, we'll have interactive Menti questions that I hope that they make the lecture fun a little. So can you please scan this QR code, or just go to the menti.com and enter this code. And if it doesn't work, please let me know. And this is also anonymous, so just please participate. So let's just start the review. The first thing that I want to talk about is AI versus machine learning. This is something that Nazila in the previous lecture talked about, but let's just see what it actually was. So what's the difference? AI, or let me type in the code again. Yeah. Oh, it didn't work. I think the code, maybe it's wrong. Let me enter another one here that I have on my laptop. Sorry about the code. I don't know how it changed. Does it work now? Did it work for you guys?
The QR code works.
Oh, okay. So the QR code works apparently. Okay. So AI is the general term that tells us how we can simulate human intelligence, but machine learning is like a subset of AI that learns from data, and it doesn't come with like the fixed rules. And whatever that we can learn with using machine learning is from the data itself. So when do we actually use machine learning in healthcare or in medical systems? We use it when patterns are too complex for humans to write rules manually, or when we have data that has some examples, like we know that's what have happened to a patient throughout time, and we have actually recorded a pattern. So that's when ML comes into play. So apparently my other code for those who are online is also working. I don't know what to do with that. 9, 8. Okay, I think the code is again wrong. I typed it wrong. I think the last one was 8.
8. Yeah, 7. Yeah, 8.
Sorry. Hopefully this one works. Okay. So if the code is currently working, I was expecting more people to be here so that they can sit together and talk to each other, but there are only 3 people. So whoever wants to participate in this one, can you please think of one real example you have seen or heard of which uses ML in healthcare? You can use like any ideas that you have seen in real life, like applications, hospital systems, medical imaging devices, and the scope has to be healthcare and medical systems. So if you have any thing on mind, let me know. Can I share the Menti to the people?
Yeah, might have to start. Oh, it's already
a start session. Let's click on this one. Okay, so there are questions coming in the chat. This one is not working.
I think it probably is working now. Yes.
Okay.
But yeah, you wanted to show them in detail. Yeah, that might be a little difficult.
Okay, so I will just read the answers to you because
just sign into your Menti here and then just like drag it here and then drag it back.
I don't know how to sign into my Menti. I forgot my login information, so I will read the answers to you. Okay, the answers are like breast cancer screening, psychiatric diagnosis, AI transcription, prediction model based on clinical and imaging features, MRI brain segmentation, and anomaly detection. Yeah, lots of good examples of machine learning. But you know, some of them are actually deep learning. And let's see what is the difference. So deep learning is not a separate part of ML, it's just a subset of machine learning. And it usually, it actually uses neural networks to learn the patterns that are very complex, like in signals, texts, and images. And it really empowers healthcare in terms of the tasks that have anything to do with natural language processing, with radiology, with understanding like the segmentations or images at like any cases. So our focus today is just on classical ML because it's the foundation for understanding that kind of prediction and evaluation as well as the bias and the other things that we need to know in order to use machine learning, because it works extremely well on the data that is much simpler. So we will start with the simpler side of machine learning. And let's review something important that we saw in the previous lecture as well, which is the types of machine learning and how the models actually learn. So we have three main categories. The first one is supervised learning. In supervised learning, the models that we use need to know what are the outputs of the examples that we are trying to predict. So when we are, for instance, predicting diabetes based on lab results, we have to actually have the results, and we have to actually be able to see what is the outcome for each patient. But on the other hand, in unsupervised learning, the model doesn't see any label and do not know what is the correct outcome. It just tries to find the pattern between the features and the inputs that it sees. So for instance, it does clustering. It does cluster patients with similar symptoms into subtypes that we can later use in other tasks. And one other thing that we won't be talking about in all these lectures is reinforcement learning, which is the type of machine learning task that the agent learns by trial and error. So the agent do not know anything, do not know what is right and wrong, and we give it reward based on the right thing that it does, and we give like punishment based on the wrong thing that it does. So for instance, we have those rehab robots that adapts based on the support level that they give to the patient and based on the patient responding to them. And in all these types of tasks, we have some other types of tasks. For instance, for supervised learning, we have two different categories. One of them is classification, which is predicting a discrete category or class. So it answers this question that, for instance, will this patient develop sepsis? And the answer is yes or no, or the answer is a category, like this person belongs to category A or category B. But in regression, we predict a continuous numeric value. So it answers questions like how much or how many. For instance, we have this question like, what is this patient's 30-day mortality risk? And it gives us like a percentage. And in unsupervised learning, we have two different types of tasks. The first one is clustering, which is clustering and grouping similar data points and identifying the subgroups as I said earlier. And the other one is dimensionality reduction, which will be shown in the slides later. And the goal of the dimensionality reduction is to reduce feature space. Because, you know, in health data, we have lots of features that might not all of them be helpful equally. So let's see what type of data that we have. So we have structured data, like the data that are in very clear tables, like EMRs, lab values, vitals, and we have images. We have time series data that in which time actually matters, and they're like in ECGs and the wearable sensors. And we have unstructured data like clinical notes and the summaries that are written, and they don't follow any specific structure. And we know that machine learning models are going to use these type of data to extract features and to actually help us solve some problems. Okay, the last review for us is the applications of machine learning in healthcare. So for applications, we have diagnosis, like detecting cancer from imaging, which uses ML and also deep learning models in ML. And we have prognosis prediction when, for instance, we say what is the mortality risk and the percentage of the readmission. And we can also do drug discovery. So the way that the drug discovery can happen is through the time that the task that ML can screen like huge libraries of compounds that can be used for making drugs. And using ML, we can predict which patients will respond to like what kind of drugs that we have. And we also have personalized medicine because of, for each patient, we can have a data that is specific to people. So by using the machine learning models, we can tell exactly how this patient is going to respond to something that we have planned for them. And we do have clinical decision support to make life easier for clinicians. And we can do medical imaging faster. And also, the other task is robotics and chatbots. For instance, chatbots, they can answer questions when doctors are not available at certain times. And that's it from the previous lecture. So now we're going to start the machine learning workflow. And the thing about this workflow is that it works for both classical machine learning and the deep learning models. So how all these things are going to happen? Well, first, the thing that we have to focus on is to define a question that is very clear. And we also need to have a goal that we want to think about and we want to try to solve it. The next part is to collect and prepare data based on the question that we have and the goal we are trying to reach. And the next one is to see what kind of features we can actually use based on the data that we have that can help us predict something. And when we have all the data, now what kind of algorithm actually works best for us? And then after working on that algorithm, we need to know how to evaluate the model that we have built to see if it is doing something good or it's even causing harm. And we will briefly see how to deploy and monitor in the real world. So let's go to step 1. So ideally, you should, in terms of talking about ML, you should be able to say, are we predicting an outcome? Is this outcome like a continuous value, or is it a category? Are we discovering subgroups? Are we ranking something? So these things helps us understand what kind of task we want to work with. When we are trying to actually figure out what kind of task we have to know what makes a problem learnable, in terms of machine learning. So before starting an ML project, verify you have all these things. You need to have a clear clinical goal. Can you state it as predict, classify, discover, or rank? And you need to have relevant and available inputs. So do you have access to meaningful features that will actually help you predict something like labs, vitals, and imaging? And what is the outcome that you are defining? Is the target that you have something you can measure? Is it clearly defined? And also, we need to have sufficient data. So do you have hundreds to thousands of examples that you want to train your model on, or you just have seen a few patients and you want to decide based on those patients? And you need to also have a clinical goal that determines the ML task type, because you probably don't have like all the time and all the computational resources to try any algorithms to see if they work or not. So the goal and the task has to be very clear in this sense. Okay, so now let's see how we can see if an ML problem is actually a good one or it is not. So a good example is like this. Given a patient's first 6 hours of ICU data, can we predict if they will develop sepsis in the next 24 hours? So in this example, the goal is very clear. So we want to see if they will develop sepsis or not. So the answer is binary. It is either yes or no. And the inputs that we have is very clear as well. We do have ICU data, and we also have like the lab routines collected, and the outcome is also clear. So we know that we are diagnosing someone based on the features and the data that we have, and the data is probably also sufficient because hospitals have many ICU cases. And another example, on the other hand, like why do patients feel better on weekends is a very poor example. The first reason is that it doesn't really look for prediction. It is asking something that requires explanation. And machine learning is not like a magical machine that can explain everything to us. It just works based on the tasks that we define. So like feel better is also very vague and subjective. We don't know what do we mean exactly here by saying like, is this person feeling better? What is better in comparison with what? And the outcome is not also measurable because we don't know how we are defining being better. And the input features are also not clear. And we don't have any like clear time frame too, because weekends is also very vague. So I want you to go to your phones again or laptops, whichever you have for your Menti questions. And I want you to tell me, is this a good ML question or not? So the first one is, why do patients prefer Dr. X over Dr. Y? And the answer that I'm looking for is that if it is suitable or not, and what kind of task it is trying to like solve. So the answers are no, 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 because it's emotion rather than fact-based. Not suitable. Exactly. Everyone is right because it is not something measurable, right? We can't see why preference is being asked. We don't know what prefer means here exactly. Exactly, right. Someone is saying that it requires explanation and not prediction. Right, because as we said, machine learning is not something magical to explain everything to us. And it works based on the task that it is designed for. So let's see the next one. Can we group diabetic patients into subgroups based on their lab trends? Is it suitable or not? And what kind of task is that? So the first answer is yes, it is clustering. Any other answers? Any other thoughts? So all the answers are saying that, oh, not all of them. Some of them are clustering. One is classification. Someone says that it is clustering because it is measurable. Okay. Okay, so actually this one is clustering. And it is a good kind of question because it says that we have lab trends and we want to actually group into subgroups based on the trends that exist in the data. So we don't exactly know what is the right choice and the wrong choice, but we know that there are trends. So we want to find them, which makes this question a clustering task. Okay, let's go to the next slide, which is the next step as well. So This step is about collecting and preparing the data. Does anyone have any questions before this step? In the chat, in the room? No. Okay. So let's see step 2. This step is about collecting and preparing the data because the quality of the model that we want to make depends on clean and consistent data. Just like you wouldn't make a diagnosis with missing or unreliable clinical information, machine learning doesn't do that as well. So what does our data look like? Let's see what its shape is, then we'll see later the other facts that we have to be aware of. So in supervised learning, one of the tasks that we'll be talking about today, the data comes with the label. So we have patient information that are the input to our model, and they give us the features that we make the models according to. And we have a known outcome for each patient, which is the label. And the label actually here helps us to understand if the model is making the right prediction or how bad it is predicting. So for instance, predicting if a patient has the flu, the features are fever, sore throat, runny nose, cough, body aches, and the label is if the flu test is actually positive or not. And in unsupervised learning, we have the patient information, but we do not have the labels for each patient. So the task is grouping patients with common cold symptoms, for example, and the features would be congestion, sneezing, headache, fatigue, and the patterns that the model might be able to find based on this data is mild cold, allergy-like cold, and cold with fever. So those are the two examples that can help us understand how model might work based on the data and the features that we have. So now that we have the data, how can we actually choose the features? And what is the meaning of appropriate features? So let's see this example. When we want to train a machine learning model, we cannot rely on all the features that we have about the patient. For instance, the features that we want to work with has to be available when we are training the model. Those features that become, those features and the data that become available after the work is done, so they're not relevant, so we can't use them in the process. And the features also have to be clinically relevant, which means that, for instance, we cannot do the prediction for someone that we want to know if they have the flu based on their eye color, right? It has to be relevant in the sense of a clinical work. And the data has to be reliable and consistently recorded. So for instance, when we want to predict whether a patient with cold-like symptoms has the flu, the relevant features would be fever, sore throat, cough, body aches, but the flu test result is not true and is not relevant feature because it is actually the label, and we don't want to give the final result to the model to get the final result. We actually want the final result. So it is not a feature that we want to give the model. And the appointment time, the time that that person has come to see the doctor, doesn't really help us make the decision, and the postal code in the records that we have is not going to help us either. So these are irrelevant ones. Any questions so far? Because we are now gonna see the algorithms. Okay, so let's talk about step 4, sorry. So now that we have defined a problem, we have gathered the data, and we have chosen our features. Now we come to step 4, which is choosing a machine learning algorithm. And this is where we pick the modeling technique to learn the relationship between those features and the outcome. And the choice of algorithm depends on many factors, as we mentioned earlier, like the type of the problem, the size and the nature of the data, the interpretability needs, like do we have to be able to explain the process or no, just knowing the outcome would be enough. And often you might try several algorithms and see which performs best. And in this lecture, we'll cover a range of core machine learning algorithms. We do not have time to go through all of them. So these algorithms have been very popular, especially before deep learning. And these are still very helpful and useful, often easier to interpret because they are simpler and they use a structured data, and we'll discuss some in the next slide. So the algorithm that we are going to talk about is decision trees that are very intuitive, and they are rule-based, which is like some if-then rules that doctors even ask. So we have random forests that are the like groups of trees all together helping us make a decision. And we also have logistic regression that uses probabilities and research scores. And we have k-nearest neighbors, which is a similarity-based algorithm. We also have support vector machines that uses separating boundaries between groups of data points. We also have k-means for clustering and PCA, which is the short form for principal component analysis in the unsupervised learning categories of algorithms. Okay. Sorry. So let's start with decision tree. Decision tree is an algorithm that is very simple and is used for classification and regression. So on the right, you can see what a decision tree actually looks like. It's a tree, a structure that mirrors how clinicians think. Here's how it works. The algorithm looks at all your features and asks which feature and which value of that feature would best separate my patients into groups. So it splits data based on some yes-no questions that it is asked according to the features. It might find that, for instance, chest pain is the most important first question. Then, for each question, it makes a branch. It goes to a yes branch or a no branch. And it continues until reaching pure groups. And as you can see in the picture, there is one node that is like the root node, which is the first question that we usually choose it as like the most important one. Then we reach to the leaves that are the predictions. So let's see the core idea behind this algorithm. So this algorithm has a core idea that is like playing 20 questions to diagnose. So what does that mean? Imagine an experienced doctor who is diagnosing a patient. So that doctor won't just randomly test everything, right? That doctor would just ask questions that are relevant and consider the features that are relevant to the diagnosis that they are making, because they don't want to waste time, money, and they actually want to get to a conclusion faster. So what do they do? They first ask a strategic yes-no questions in order, like, do you have chest pain? And this question definitely answers better than what is your eye color. And I'm sorry that I mentioned eye color a lot, because I thought that it's very irrelevant, so it just comes to my mind a lot. And so each answer narrows down the possibilities. When they ask if it is chest pain, the answer would be yes or no, right? So when it is yes, it is more closer to cardiac issues, and if it is no, they will look for other causes. And they will stop asking questions when the answer becomes clear. So when they are confident in their diagnosis, they won't go any further. And this is exactly what a decision tree does. It learns the best questions to ask and in what order. So let's choose the best question to ask. Please go to Menti again. We have a scenario here. You are diagnosing patients in the ER. You have 100 patients, 45 have bacterial pneumonia, and 55 are healthy. Your decision tree needs to ask one question first. And the goal is to separate pneumonia patients from healthy patients as clearly as possible. So now you have four options. Does the patient have a fever? Is oxygen saturation less than 92? Does the patient have a productive cough? Is patient over 65 years old? Which one do you think has to be the first question? So these two have the most votes. Does the patient have a fever, and does the patient have a productive cough? Actually, this question doesn't have one true right answer, and it all depends on the data that we have. Let me tell you why. So, for instance, in the data that we have, for people who have fever present, the pneumonia number is 57%. And those who do not have fever, 17% of them have pneumonia. And in each cases, there are 30 healthy people and 25 healthy people. So, the groups are not very separate and they're still mixed. So we need more and more questions to figure out if this person has actually the problem that we want to diagnose or not. But in the data that we have, for question B, which is about oxygen, 42 people have pneumonia when their oxygen saturation is less than 92%, and only 8 people are healthy. So the pneumonia percentage here is 84%. And for those who do not have this problem, 6% only have pneumonia. And for the next ones, again, the percentage for pneumonia is very close. And for the other one is also the same. So decision tree, if it sees this kind of data, it will go with oxygen because it is the most pure one in order to get to a result. So here, the oxygen will be the first question that it asks. And now out of like 84% of the people, it can probably figure out the other conditions much, much faster. And so let's see a decision tree without just one question. So this decision tree helps us with classification. Imagine you have some features that are collected. These features are chest pain, pain radiating to arms, and the age of the person, and the label that these features have, and you want to also predict, is having a heart attack. So imagine that a decision tree has chosen the chest pain as the best question to start with. If the answer to this question is no, it means that there are some people who do not have chest pain. So they will be labeled as low-risk patients. So they will probably not have a heart attack. And for those whose chest pain has been identified yes in the table and the features that we have, it asks another questions. Is the pain radiating to arms? If it is yes, it is definitely high risk. So decision tree will label that person as a person with a high risk heart attack. And if it is no, it will ask another question. Is that person older than 65? And if it is yes, it is definitely high risk. It doesn't matter if the pain is not radiating because of their age. It is still high risk because in the data, those kind of patients have been identified with heart attack. And if it is no, it is again low risk because in the data, we have seen that these types of patients did not have heart attacks. So when a new patient comes, this decision tree helps us see what is probable to happen to them. And this is actually how ML work in this case. And I'm going to show you one regression example as well. These are the same features, but here we want to predict something that is a number, a continuous number. It's not a group, which is the length of a stay. And in this case, the answer won't be like high risk, low risk, or yes or no. And it's just a number that we can get it by averaging the numbers. So here, the tree works the same way. It asks questions like, does the patient have chest pain? Is the pain radiating? Is age higher than 65? But at the leaves, we have the length of a stay. And the thing that happens here is that based on the length of a stay that the previous patients have, when we follow like the branches and we have different lengths of a stay, we average them all and they become our leaves in these kinds of trees. So whenever a new patient comes, we see if they have the similar pattern and the length of a stay would be the same thing as well. So when to use a decision tree? The strength of the decision trees are that they are highly interpretable. So they produce a flowchart of yes/no questions. So we know exactly how we got to a decision. We can see the process very clearly. And this maps perfectly onto how clinicians already think. And because of this transparency, decision trees are great for clinical settings where we need to justify and explain a model. And they can also work with mixed kind of data. So we can have like numbers or categories like age and yes or no for chest pain, as we saw in the example. And they can also capture non-linear rules, which means that there is a combination of conditions that is important, and it is not just one single trend. For example, a patient might only be high risk if their age is greater than 60 and chest pain is radiating and blood pressure is low. So this is not a linear combination probably. And there is not just a straight rule that we can show a patient pattern with, and decision trees can handle that very naturally. And they're very quick to train. So they are usually used as baseline models for greater models in machine learning. And the problems that they have, the first one is that they are prone to overfitting. I haven't explained overfitting yet, but I will. So for now, just know that overfitting means to memorize one patient or several patients' information not learn based on them. And I will say what that means later. So one of the problems is overfitting, and they're unstable. So any changes, any small changes the tree as well. And they struggle with high dimensional data. So when the data is very large and the number of features are also very large, it finds it hard to find the patterns. And it is usually weaker than other methods that can put together several decision trees rather than just one. And so the next algorithm that helps us overcome some of the limitations of a single decision tree is random forest. So random forest is an algorithm that again is used for classification and regression. And what it does is not to use only one tree, instead to use many trees and let them all vote. So it's one of the most successful machine learning algorithms in healthcare. And if you look at the diagram, you can see that random forest creates hundreds or even thousands of decision trees. But the clever part is that each tree is trained on a slightly different random sample of your data. And at each split, each tree only considers a random subset of features. So each tree, after seeing all those features, votes on a prediction, and the final answer would be the majority of the vote for classification. And for regression, it is just averaging the votes. Here, it is the core idea of random forest, which is just like consulting multiple doctors. So you wouldn't trust just one doctor's opinion for a serious diagnosis in real life, right? You will probably ask more doctors to see what they think. And this is just like random forest. So in random forest algorithm, it gets multiple expert opinions, like 5 different doctors examine the patient independently, and each doctor has a slightly different experience. For instance, Dr. A is very good in imaging, Dr. B focuses on lab work, Dr. C relies on patient history. And each makes their own recommendation. So each doctor might say, surgery, surgery, medication, surgery, surgery. And you see all those answers and see, okay, 4 out of 5 say surgery, so my final decision would be surgery. And this is exactly what random forest does. It builds many expert decision trees and takes a vote. So let's see this example. The goal here is to predict if a patient will be readmitted to ICU within 48 hours. And the features that we have are vital signs, lab values, medications, nursing notes, sentiment, and the label that we have here is being readmitted, which is yes or no. So the data set that we have has lots of features, but we said that the trees that we make for random forest use different types of features. So a little different. So for instance, in the first tree, the focus would be vital signs and the age. And the next ones use different features. And finally, they all vote something, just like how we saw decision tree votes on something and predicts something. So now that we have all the votes, we aggregate them and see which one is more likely. In this scenario, the final prediction would be yes, because 68% of trees voted yes. So this new person that comes will be probably readmitted because the features that they have matches those that have been readmitted before. So let's see when to use a random forest. The first strength is that it is very accurate, much more than a single decision tree, because by combining many trees, we can detect patterns that one tree would maybe miss by focusing like only on one feature at a time. And the second one is that it can handle complex, it can handle missing data very well. Because, if there are some data missing, the decision tree cannot understand that well, and it will just focus on predicting based on the features that it has. So when the random forest tries to use features differently and not use all of them at the same time, it can actually handle the wrong features and the missing ones better. And it also provides feature importance ranking. So when like the risk increases only when age is like higher than 70 and the fever is greater than 38 and the blood pressure is low. We can see how the trees are built in like an ensemble of trees, and we can see which features have been most helpful, so we know which are more important as well. And it can also work with different types of data, just like decision tree does. And now we can have a break before seeing the next algorithms, if that works. Oh, how long do you want to break? Like 10 minutes? Or 5 minutes, 7 minutes in between? Yeah, 7 minutes. Okay, what should I do? Okay, I will mute the Zoom then. Be back in 7 minutes. So I'm back. Hi, everyone. Let's continue with K nearest neighbors, or KNN. So KNN is perhaps the simplest machine learning algorithm conceptually, and it is pure case-based reasoning. The entire algorithm says, show me the patients who look similar to this one, and I predict they will have the same outcome. So what it does is storing all training examples in memory, and for each new patient, find the K most similar patients. If you look at the plot on the right, let's say the green or blue dots are the patients without diabetes, and the red ones are the patients with diabetes, and we are plotting them based on two features, maybe age and heart rate. And when a new patient comes in, like the white one, we don't know if they have diabetes yet. So KNN says, let me find the K most similar patients. If we set K equals to 5, we draw a circle around the 5 closest patients to our new patient. We find like all the 4 blue points inside that circle, and the majority vote would be blue, which is no diabetes. And that's it. Like there's no training phase where we learn rules or build trees, and we just measure similarity using some kind of distance metric in our feature space, according to our feature space, and we predict most common label among neighbors. And here, the core idea, as I said, is finding similar past cases. So for instance, if you want to diagnose a new patient, you just look at similar past patients. You find patients who look like this one. And what does that mean? It means that they have similar lab values, vitals, and symptoms. And you see what happened to those similar patients. So did they have like iron deficiency, thalassemia, or B12 deficiency? And you take a vote among those neighbors. If 6 out of 7 similar patients had iron deficiency, probably it is a problem. And there isn't any complex training needed, just to store the past patients and search for matches. So KN is like asking who are similar, as we said before, and let's see what we can do here. So let's go to Menti again. So if you wanted to diagnose a patient, how would you do that? You're diagnosing a patient with anemia, you have their lab results, which are these things written here, and you have a database of 1,000 past patients with known diagnoses. So how should you use past patient data? The first option that you have is to find the one most similar past patient. If they are very similar, you use their diagnosis. Or if you find 5 to 10 most similar patients and take the majority diagnosis, or you average all 1,000 past patients' lab values and compare them. Which do you think works better? Most answers are for finding 5 to 10 most similar patients, and there are answers for averaging all 1,000 past patients. Okay, so what is the correct option here? Okay, so if you just look at one patient, the option that nobody chose, we are doing something very risky. So for instance, if that patient is patient number something, and this is the feature that we have for this patient, and the diagnosis for this patient is iron deficiency. What if that person was actually misdiagnosed or something was unusual about that person? So it's very risky to rely on just one example like that. And if we choose all patients, it includes patients with very different labs as well. So those 1,000 patients might have very different features, and we don't want to consider everyone to make a decision, right? We want to consider those that have had similar lab values. So for choosing answer B, we can justify it with, like, if we find 7 patients with closest lab values, we have like a strong claim here. We can say that if most of them have iron deficiency, then this one has iron deficiency as well. Even if 1 or 2 are wrong, the majority is still correct, and this algorithm relies on that. So there is a question in the chat that says, are there temporal elements to the nearest neighbor that will it match the patients at the point of diagnosis or at some stage of their condition rather than just their current state? Is the patients at the point of diagnosis. So temporal elements, they can definitely be used if they are in the data and they are an important feature to consider. Otherwise, no. But you know that temporal elements can be a part of features, because if they have any effect on a person's diagnosis, so it is recorded and it is important. So it can be here as well. It doesn't matter what types of features we have for nearest neighbor. We can rely on the records that we have. Okay, so just like what we saw, we can have features like this, and the labels can be lots of different things, and we don't really care about that. We don't care how many of features or how many of the labels do we have. We just want to see how do they look like if they're similar. So if a new patient comes, which is a 62-year-old woman and has the features, as we can see in the bigger circle in the middle, we try to use a metric that makes sense. For instance, if the thing that we want to compare is a number, we will use some number metric to find the distance between these two numbers, like HGB, MCV, ferritin, and TIBC. And in this feature space that we have, we see that most people have iron deficiency, and this person is diagnosed as the one with iron deficiency as well. But one of the questions that we need to consider while working with KNN is that how many neighbors should we actually consider? As we saw in that example, one example is not enough. It is too small because we cannot make a prediction based on one single nearest patient and rely on that and make sure that this person wasn't misdiagnosed. And it is like very sensitive, and that's one blue patient might be a misdiagnosis. I don't know where this blue came from, but that patient might be a misdiagnosis. And the result is usually overfitting and unstable that we can't rely on. And if it is too large, if we have like too many patients, including the ones that are very distant, it is also problematic because it includes patients who aren't actually similar to, and it feels like averaging many people that have lots of different features. and trying to make predictions based on things that are not necessarily relevant. So we have to choose something that is in the middle, and we can try different cases when using this algorithm to see which one is working better theoretically and based on the experience. And the strength of this one is that this algorithm is that it's very intuitive. Clinicians can immediately understand what it means and what it means to find similar patients, and it doesn't require any training. And it is called lazy learner in machine learning as well. Because we don't build any equations, any trees. The model only works when a new patient arrives, and it works well with similar data sets. So many healthcare data sets are small and can and performs nicely in those cases. And it is a similarity based. So it naturally tells you the outcome even if you're not like very experienced. And yeah, it can handle multi-class problems naturally as well, like the one that I showed. It doesn't matter how many labels and how many classes do we have. We can still use this algorithm. And the weaknesses is that it is slow for large data sets because for every new patient, the model compares against every previous patient based on the K that we choose. So if the K becomes very large for very, very large data sets, it takes time. And it is also sensitive if the features are irrelevant because we are considering all features for those people that are similar. And it struggles in high dimensions. So with too many features, everything starts to look equally distant. And it also is hard to explain why certain neighbors is like close, because you can see the neighbors, but explaining why they were mathematically close isn't always very intuitive according to the metric that we choose for the similarity. Now let's see the next algorithm. It is called logistic regression, one of the most widely used algorithms in medicine. Unlike decision trees that give you rules, this algorithm gives you probabilities. This is very valuable because you can tell a patient, like, you have a 72% chance of developing diabetes rather than just telling them that you are high risk. And if you look at this diagram, we can see that there is a curve that comes from the sigmoid function. So whatever feature that we have, this algorithm gives a weight to the features, and it gives a formula of the weights and the features into the sigmoid function, and the sigmoid function outputs a probability that is between 0 and 1. And what it does is to draw the best separating line between two different classes that we have. And it also converts the probability to two different classes. So the probability that we have based on a threshold turns to be like yes or no, or this category or the other category. And it is great for risk scoring models. Let's see how and why. So the core idea of this algorithm is building an automatic risk calculator. So you have seen risk calculators in medicine. They give you a percentage. For example, a doctor fills in the table that they have for a patient, what is their age, blood pressure, cholesterol, smoking, status, and each factor adds to the risk of the thing that they want to diagnose. And the calculator of this algorithm outputs this patient has 27% risk, which is not just yes, no, it is an actual percentage. And for a doctor, it is like when someone decided how much each factor matters. if you want to compare it to this algorithm. So each of these factors, like age, blood pressure, and etc., have a level of importance. So for instance, in order to figure out what is the risk for this specific person, the age can add 2 points to the formula, smoking can add 5 points, and etc. But how can we decide these numbers for logistic regression? So usually experts and doctors create these types of formulas by hand, but logistic regression does this automatically. It learns the formula from the data, and the way that it works, we will see in the next slide. So before that, let's see what we have here. So we have a scenario here. You want to predict heart attack risk using age, exercise, blood pressure, smoking status, and the goal is to understand how logistic regression assigns importance to different risk factors. So we want to understand that, but I have a question for you. Which risk factor do you think matters most for heart attack risk? So what do you think? Which one will be like more important if you were a doctor? So age is important. Again, age. Blood pressure. Blood pressure again. Age. Okay. So, we have some intuition about what can be important, right? But logistic regression, which is just a mathematical algorithm, doesn't know that. So the way that it works is considering, like when we say that it learns the optimal weight for each factor, and it learns from the patterns in the data which one matters more, it means that it just goes through the features that exist in the data and randomly assigns some weights to these criteria and these features that we have. So for instance, clinically, we know that smoking is a very strong predictor. Age is also very strong, and high blood pressure is moderate, and exercise is actually something protective. So what happens here is that first, initially, some random weights will be assigned to all these features. And the model makes a formula, give it to the sigmoid function, and checks whether it is actually predicting the patients according to the labels that we have for the patients. And accordingly, it tries to make the weights better and better over time. So eventually, we can have something like this. So we have lots of features for this patient, and we have this label that says cardiovascular event in the next 10 years. So the risk factors and weights are shown on the left side that the model has been trying to predict according to the labels that it has. And this patient's score is 27% that comes from the sigmoid function. And here there is one important thing to note. So when you are trying to predict something, you need to give a threshold manually to logistic regression. So for instance, in this example, I have chosen that if a person's weighted score is higher than this 20% threshold, then does action 1, otherwise does action 2. And as you can see, the model output is higher than the threshold, so the decision is choosing this person as like the person who has a high risk for cardiovascular event in the next 10 years. And how do we choose actually this threshold? This threshold cannot be too low, because if we consider a number, at least like something that is not a number that makes enough sense in terms of our clinical predictions, it might just flag many patients as high risk. And it means that we will have too many patients that have been considered as positive cases, while it has been false. And also it causes like lots of problems like overclocking risk, unnecessary tests, low precision, that we'll see what it means later. And also on the other side, if we choose a very high threshold, it only flags very high probability cases, and many true cases that do not reach that will be missed. And early patients fall below the threshold, and we will have no alert for them. And it is kind of dangerous, because if that person requires doctor's attention and follow-up, they will miss that according to our algorithm. So the strengths are producing probabilities. It is very fast and lightweight. There are a few parameters which are our weights. And it is considered a good baseline for risk prediction. And the weaknesses is that it only captures linear relationships based on the formula that we have. And it is poor at complex interactions, which we had a better version in trees. And it is sensitive to features that are on a scale, because we assigned weights to the features. And if some features are much bigger compared to the other ones, they have much more effect, which might not be fair, and it can be misled by outliers. So let's see, where should we? Okay. I'm thinking of skipping this algorithm for the time. It'll be fine. It's so long. Okay. Hopefully we'll be okay then. So the last algorithm that we'll talk about in supervised learning algorithms, it is this support vector machines, which is the algorithm for using support vectors to separate two different categories of data points. So what it does is to find the best separating boundary. It maximizes a margin between classes, and the support vectors are the key data points here and can handle nonlinear boundaries. So as you can see in this thing that we have here, these points that are closest from each category to the other category are called support vectors. And a space that is between them is called margin. And the goal of this algorithm is to maximize this margin based on the support vectors that it finds, and draw a hyperplane that is a boundary. So anything that falls on this side of this hyperplane belongs to this category, and the opposite is for any point that comes here. So the core idea is something funny that I found online, that the core idea is like inflating a balloon between two groups. Like the thing that happens is that there are two different groups and two different data points. So we inflate a balloon as much as we can until we keep expanding it until it touches closest points on both sides. And the patients that touches this balloon are called those support vectors. And let's imagine separating two groups and see how it actually works. So we have healthy patients on the left and sick patients on the right. And we don't want a boundary that barely separates these two, because we want to be confident in the boundary that we are putting in there. So any new patient that is a slightly different will change the prediction if that boundary is not accurate. So that's why we inflate that balloon. And the SVM makes that boundary for us, and the edges that we have from each group that we call support vectors define this boundary for us. So this is how SVM works, which is a little different compared to other algorithms. But before I show you the complete example, I want you to think like this algorithm does. So let's see another mentee. I want to know, where should we draw the line? So we have this scenario that you're separating healthy patients from sick patients based on lab values. We can draw the boundary line anywhere between the two groups. Where should you draw it? The goal is to understand why SVM maximizes the margin. So we will draw it close to the healthy patients, or close to the sick patients, or right in the middle with maximum space on both sides. Okay, we have answers for all the groups. Think a little more. Okay. So if we go with option A, which is close to the healthy patients, there's a problem. So when a new healthy patient is slightly off, it will be misclassified. So the boundary is a little unstable, and there isn't enough room for variation in the features that we have for patients. And also, if we draw a line that is close to sick patients, the same thing happens. So when a new sick patient is slightly off, they are classified as healthy. And again, there is no room for variation, but if we draw something that is in the middle, with the maximum space possible between the two groups that we have, and is far from both, there will be room for natural variation in the lab values that we have, and it is the most stable choice because the small changes won't flip the prediction and won't misdiagnose and misclassify people. So this is what SVM tries to do. So in this example of how SVM works, we have two features that we collected. So we have a two-dimensional space of features that we are trying to draw the diagram in. One of them is the tumor size, and the other one is mitotic count. And the label is benign vs malignant tumor. And for patients with known diagnoses, we have the numbers and the labels according to the features that we have. So if you look at the right picture, we can see that the blue ones are the benign diagnosed patients, and the red ones are not. And also you can see one blue dot, sorry, these are dots, and those are not dots. One benign is outlier, because whichever line that we draw, we couldn't separate that one correctly. So instead, the focus is on those patients that are closest to the other group. And these are the support vectors, and these two actually maximizes the margin that we have between these two groups, and the line that is like right in the middle of this margin is the one that we are looking for, and it's called the decision boundary. So when do we actually use SVM? SVMs are very effective in high-dimensional spaces, like genomics or imaging features. And they're also memory efficient because they only store the support vectors. They don't do anything with like the other patients that are not the support ones. But it's not but, and they work well when classes are clearly separated. Like we do not have too many outliers and we do not have very ambiguous data. And they're also resistant to overfitting because they do not memorize like all the features and they don't work based on them. And the weaknesses that they have is that they're slow when the data sets are very large, and they also do not directly give probabilities. They need extra work for that, so they don't work like logistic regression, and they're hard to interpret because we do not know exactly why it decides to do something that it does at some points, and they're also sensitive to feature scaling. Okay. This one was the most complicated one on the side of supervised learning, and we will only see two from unsupervised learning now. The first one is k-means clustering, which is a clustering algorithm. And we do not need any label here. And the thing that happens here is that the patients that are similar will be grouped together. So we specify a number, which is the number of clusters that we want to make the subgroups according to. And the thing that this algorithm does is to discover the subgroups that naturally exist in the data. And there aren't any predefined categories, so it just finds the patterns itself. The core idea is to find these types of subgroups that are naturally there. So imagine you have 100 diabetic patients. They all have diabetes, but respond differently to treatment. So some do well, some others struggle. You suspect there are subgroups. So they all are diabetes, but there might be something else for grouping them. But you don't know what they are or how many subgroups there might be. So you group patients by similarity in their data, right? You just look at the data and you see, okay, there are patterns in blood sugar, in BMI, or in medication response. And the natural groups emerge according to the data. So one of them might be well controlled, the other one is medication resistant, and the other one is newly diagnosed. So k-means does exactly this. It discovers hidden patient subgroups. So when you have an example like ultrasound features of thyroid nodules, you might have all these features in your data set, and you don't have any label, so you don't know what you're doing is according to like any true classification or regression. But what you care about here is to just find the similarities between these features, which leads to similarities between patients. So first, on the right, you initialize like 3 centers for the clusters that you are making, and you assign data points that are closest to these 3 centers. And this closeness means that the features are actually close to each other based on a metric. And then you recalculate the centers. So what you do is to make new centers based on the features that are close to each other. And the center moves, and you repeat this process over and over again until it doesn't like change anymore. And eventually you might have something like cluster 1, which is low risk, cluster 2 intermediate, and cluster 3 high suspicion pattern. And they all can have some of these features in a different way. So the cluster 1, which are low risk, have a small size, smooth borders, and no micro calcifications, and some other similar features for other clusters as well. And so when should we use this algorithm? Oh, before talking about that, sorry, that's the wrong slide. Before talking about that, we also, for this one, needs to know that we have to choose a K. So the K, like the other algorithms that had this K included in them, it cannot be too few because the prediction might mixes very different patients into broad groups. And the problem is that the low risk ones and the high risk ones might just get mixed together. For like the previous example, the one that are benign or suspicious, or the other categories, they all might fall into the same. So we might actually lose meaningful subtypes. And here in this case, we call it underfitting because we are not doing well in training our model. And if it is too many clusters, it might create very tiny microgroups. And the problem here is to not being able to interpret what is happening exactly clinically inside each group. And an example might be a slight variations in size or texture become separate clusters, which might not even be the true case. And the result here is overfitting, like memorizing all the features that we have without them giving us enough information that is actually useful. So I have a question here. Without a predefined label, how are the clusters named after running the algorithm? For example, in the prior example, how are the masses defined as high risk or low risk? So let's go back to the previous algorithm. So the thing that happens here is that we do not actually know these labels, but when they are being used by experts in this domain, after seeing like these people have been responding the same, or they have been prescribed the same things, and like seeing the results of the clusters that we have, we can actually, the expert can actually tell if these are low risk or high risk or medium risk. But the thing that happens with the machine learning side is that we do not really know the names. We just know that these patterns has been seen, or these patterns has been similar. So these labels that I put here are not given to us by the machine learning algorithm. So when to use k-means clustering. So the strength of this algorithm is that it is very simple and it is like intuitive because it just works based on the features and the things that exist in the feature. There are no weights and no formula or anything like that. And they are very fast on large data sets, and they can scale well to many features. And they discover hidden subgroups without labels, which is the actual definition of this algorithm. And they're great for exploratory analysis. And the weaknesses are, we must specify K in advance. So we might lose information because of the K that we choose. And they're also sensitive to initial centers that we choose. So we might put them something wrong and it might cause us problems. So they also assumes clusters of similar size in similar shapes, which might not be always the case. And they're also sensitive to outliers. So if there are like some centers that are being changed according to some irrelevant data, we cannot do anything about it. Mhm. Okay, and I wanted to mention something very important in unsupervised learning that we use. So in medicine, we often measure too many features. Like we have so many things, and many of them are kind of connected to each other. And these too many features that sometimes overlap make the models harder to understand, harder to visualize, more prone to noise, and slower and less stable. So we have an algorithm in unsupervised learning that is called PCA. And this one reduces all the huge features that we might have into some principal components that capture the most important patterns. I have to be a little quick here because we don't have much time left. And I wanted to talk about the evaluation part because I feel it is more important than all the algorithms. So I will show you this example very quickly of how PCA actually works. So we have these features collected from wearable devices. And the problem here is that these 7 features are highly correlated, and they all measure aspects of sleep quality. So what this algorithm does is to takes these high dimensional data that we have for each patient and check how they are actually related to each other. So the thing that happens is that it assigns some weights to all the things that happens in the feature space, and it compress the feature space into the ones that are the most important. And the most important features come from the combination of the features that are related to each other. So for instance, this patient A has 7 features, but eventually it will be converted into 2 feature space because PCA can like make PC1 based on assigning a weight to a sleep, assigning a weight to the deep sleep, and assigning a weight to awake time, and make another feature which is called PC1 and make another feature as well that is called PC2. And the thing is that it considers all the components, but it considers different kinds of weights to like prioritizes the features differently. And then we can only have one number in the end to compare in the algorithm. So it's a little complicated to explain more, but I will try to like share the slides with you so you can see them later. I will skip this one as well, and I will just talk about the evaluation, which is very important in healthcare because in healthcare, machine learning can do many harms to patients because wrong prediction can actually harm the patients, and the misdiagnosis can delay treatments, and the false alarms can cause like alarm fatigue and lots of costs, and the biased models can cause health disparities. And we need objective evaluation before clinical use of any of these algorithms. And there are some questions we must answer, like how accurate is the model? Will it work on new patients? And can we trust its predictions or not? And one of the most important things that we should know is the term overfitting and underfitting that we also mentioned during the slides. So overfitting is just like the pattern that we see on the left side of this diagram. So the thing that is happening on the left is that the model learns training data too well. which we do not need. Actually, it memorizes the specific examples instead of the important patterns. So it is very good on training data, but it is very poor on new patients. And the risk here is that it might work in your hospital, but you cannot see it as a generalizable example elsewhere. And on the other side, we have underfitting, which means that the model is too simple to learn patterns. And it even fails to capture important relationships in the training data itself. So for instance, on the right side of the diagrams, we need like a curvy line to separate the blue dots from the orange ones. And a straight line is just too simple. It cannot capture all the information that we need. So finding the balance is very important here. And the thing that we can do about it is first to skip this slide and catch overfitting by using train and test split idea. This is like the thing that is used in all machine learning algorithms. And the idea behind it is that we make a set of data that is called training set, and it consists of the practice problems that we have. So we divide the data that we have into two groups. The first one is training, which is like 60 to 70% of the data. And there is the test set, which is like 30 to 40% of the data. And to just give you an intuition about this one is like, imagine you have a students that learn from 700 practice cases, and the model learns patterns from training patients, just like the students learn from practice cases. So we can check progress, but this doesn't prove mastery. Like if you keep reading the practice cases over and over, you will just learn those practice cases. But we need to actually test you, right? So the student have to be tested on the questions that they have never seen before. And it is the same for training and testing our model. When the model see the data, it has to now be tested just to see how it works on the data that it has never seen before. And this is the part that reveals the true understanding. So, you know, if the students saw the exam questions before, do they do great? Yes, they probably do great, but did they actually learn? We don't know that. So we should never use all the data that we have to train our model. We should keep some for testing to see if it actually works well. And they have to just skip these ones as well. I think the time is over, right, Ken? Okay, so I really liked these slides, but I think you can read them for yourselves as well. And like, okay. This is the end, right? Okay. Let me see. Okay, so thank you for listening and for coming. And this is the QR code for attendance and feedback, as explained earlier. What happened?
Yeah.
Really? Okay, it is deactivated. Yeah. Please wait. I didn't have the time, but I wanted to mention that I created my images with AI. And it was very fun, like especially these images. They all are created with Banana Pro. And I could just give them the story, and yeah, that was all that it could make. These ones as well. Is it right? The link is for attendance is in the chat. I can access. I think the link works in the chat. The QR code isn't activated, right?
I don't know use for it, so I don't know.
So our QR code is not gonna work probably.
I didn't realize, I guess there's a 7-day deal. I guess a 7-day.
Okay, we lost our free version of QR code, that's why.
I don't know how the first one. But I guess note to self, check on the data.
Can you guys use the link instead? You said we have a survey too. Is it different than this one? You said we have a survey?
Oh, everything's linked into one.
It's the same thing. Okay. Oh, so this link is attendance, feedback.
So we encourage the students to have feedback.
Okay, so please leave us feedback. Good feedback. Good feedback. Gonna make us happy only, yeah. That's the only point.
Oh my god.
No.
Wait, the form says session one?
Like the title of the session too, but I couldn't do the attendance as my attendance session one.
I
don't know if I have my digits on it. You guys can base that it was submitted.
Yeah, it should be fine. I think I just forgot to edit that, but thank you for letting me know. I will change that in the future. I am very sorry about the confusion.
Does this like replace anything or no? It's gonna keep that one as well. The session one.
Oh no, it's a new form. I changed everything except I believe what he was referring to as a submit. I have a submit message, and I think I forgot to change the submit message.
Oh, okay.
But like otherwise,
okay.
the details should be correct. You can probably
Okay. So I just wanted to show you this wrap-up too, even though we don't have time to go over evaluation. If you like, I really recommend you to do so, because that was interesting to know. So what we saw here today was turning clinical questions into ML problems and meet several classical ML algorithms. And we saw a little about how to judge a model, and the algorithm is only one piece. So there is a workflow that we have to consider if you want to use ML. And the next step be deep learning models that learn their own features from images, text, and signals using the same principles you saw today that will be presented by my dear friend. And that's all. Thank you so much for coming, you two and all the people in the Zoom, and hope to see you again next session. Bye-bye, everyone. Stop the share.